Can you see the PowerPoint?
Yes, sir.
So let us start now. So name of the experiment is study of DC servo motor characteristics. There are a few important keywords in this title of the experiment. So we are going to study, okay, study the characteristics. Characteristics of what type? Characteristics which are important for control system design, okay. So and it's a DC motor, and there is a keyword servo. So this is a DC servo motor. So the total phrase DC servo motor implies some special meaning, and in this experiment we are going to study this kind of special motor, okay. Its characteristics, various types of characteristics. So these are the points I'm going to discuss. What is servo system, significant aspects of servo motor, necessity of determining the characteristics of DC servo motor. So from these 3 points, you will understand why it is special, and regarding the experimental setup, procedure, and data, etc. So servo system. So this is a typical example, schematic diagram of a servo system or servo mechanism. Servo mechanism is a feedback control system, and it is quite common in machine tool applications, where you need precision motion control. Not only machine tool, but also in various other industrial applications and robotics, particularly. Robotics, all mechanism or robotic mechanisms are controlled by servo systems, or servo mechanisms are employed in robotics for its control, position control, velocity control, pose control, like that, and interaction with the environment. And also in space science, for controlling the various location of the antenna, in order to control the motion of the rocket or the space vehicle, you need some servo mechanism to appropriately position the nozzles through which the exhaust gases emit to produce motion as per Newton's third law. So if you see any video from available in YouTube during the rocket launch, you'll find that the various nozzles, the position of the various nozzles are controlled to control its direction of motion. So they are actually implemented using servo system. So servo systems are controlled. Actual control action or force or torque is applied through various types of mechanisms, like hydraulic systems sometimes, where a lot of force or torque is required, as it happens in case of aircraft landing system. The precision position control of the various components of the aircraft wing. So they are controlled by hydraulic system. So they are called hydraulic servo system. And various other applications, and pneumatic systems are also applied. And depending upon the nature of the actuator, type of the actuator, it is called pneumatic servo system, hydraulic servo system, electrical servo system, like that. So where DC motors are applied in a servo application, servo mechanism, there it is called DC servo motor. Now, why the keyword servo is there? Servo, this word appeared or originated from the word servant. That means whatever command we will give, it will help to follow that command it will help the mechanism to follow the command. So actually it is the main you can say component which is implementing the motion, or it is the key system, the main system which is actually implementing which is actually responsible, you can say, to impart that force. That is my point in the system. So in that sense, it is a slave, okay, servant. It is following the master. So DC servo motor is a type of motor, DC motor, which is used in motion control applications. There is a precise description of a DC servo motor. Now, so here it's working in closed loop. We are applying some command. We are applying the command, and the position control unit is helping the servo drive to follow that command. Okay, and drive actually is the power source through which the motor is getting the power in order to operate, because the control system, the position control system, which is taking reference input and feedback input. Feedback is taken from some speed sensor or something over here, and it is generating control command. But that control command is basically a signal which cannot drive a motor, So therefore, we need to amplify that signal to bring it to the power level. So after we bring it to the power level, then we can apply it to the armature of the DC motor over here, and it will produce necessary torque, because torque is proportional to flux into flux density, or flux into armature current. So it is called, in servo mechanism, it is called servo drive, because it is giving driving capability. That's why it's drive. Or in other literature, it will be called servo amplifier. Basically, it's an amplifier. Now, this is the basic block diagram. We have already seen this type of diagram in the textbooks, and the diagram at the bottom of this PPT is a servo system, position control servo system. You will learn this position control servo system in the next year. Now, the detailed block diagram is same as a generic feedback control system. Input command or reference, feedback. We are taking feedback, okay, from the servo system, and the error is generated after comparison, and we are using control system or control element. Control element is producing control input, which is amplified through driver and fed to the process or the servo system. And here disturbance input, which may be the shaft loading in case of DC servo motor, and noise in the feedback, maybe measurement noise. So here it is output variable. Here it is measurement signal. Here it is reference signal. Here it is error signal. Here it is control signal. Only this part is power. This part is in power level, and this is physical variable. So here, in case of a motor, it will be mechanical output. That means either position or velocity or acceleration. But this side is electrical signal. So you have to convert that non-electrical quantity, here it is mechanical quantity, to electrical quantity, electrical signal. So you need an appropriate sensor, which is a feedback, which is depicted over here as feedback element. Do you know the difference between transducer and sensor? There is a misconception that we need transducers here to feedback. No, we need sensors. There is a distinct, or you can say definite difference. Okay? Definite difference between sensor and transducer. A transducer is just one element which converts one form of energy to another form of energy. Nothing more than that. Nothing less than that. Okay? It only converts one form of energy to another form of energy. It has no other functions to perform. But a sensor can make ready measurement, can give you ready measurement. It may contain a transducer within it. It may contain a transducer within it. How? Suppose you want to measure the body temperature. So there are two choices. You can purchase one electronic thermometer, which is quite common nowadays. In the medical shop, you can ask for a clinical thermometer, electronic thermometer, or you can buy a thermistor. But because you studied transducer in your engineering curriculum, so you can say, okay, I am an engineer, I am an would-be engineer, so I'm not going to follow the conventional measuring technique, so I will measure with my own device. So you purchased one with a lot of expectation, you purchased one thermistor and you wanted to measure your body temperature. Is it possible? Possible, provided you perform few operations with that transducer. First of all, you have to characterize your transducer. You have to find out its characteristics, temperature versus volt versus temperature characteristics, voltage generated versus temperature characteristics. If it is nonlinear characteristics, then you have to provide, you have to add some circuit to linearize it, because nonlinear measurement with nonlinear system is not so easy. So you have to linearize the characteristics. Then if it contains measurement noise, then you have to filter out the noise. If the voltage generated is so weak so that you cannot perform A to D conversion, or it does not match the input range of the A to D converter, the input scale of this. So you have to make some level shifting, some amplification. So all kind of signal conditioning. All these operations are called signal conditioning. You have to perform signal conditioning. And finally, after all signal conditioning, if the signal is okay, finally it's okay, it can be converted to digital one, to connect it to digital display. Then you have to calibrate it finally. Until and unless you calibrate a device, you cannot make measurement with that. So after all such operations, after addition of all such circuits and operations, okay, you can use a simple thermistor, which is a basic, you can say, transducer for measurement. So mere a transducer cannot perform measurement. You have to add something as per the requirement for measurement. The final step is calibration. You have performed everything, but you didn't calibrate. Then also it cannot be qualified as a sensor. So there is a definite difference between sensor and transducer. In interview, quite often it is asked, what is the difference between sensor and transducer? So if you do not know this fact, probably you cannot answer. So a sensor can make ready measurement by virtue of its internal circuits to perform signal conditioning, as well as its calibration, prior calibration. It can make ready measurement. So here, if you say that it's a transducer, possibly the interviewer will understand that you are half engineer, not a full engineer. You lack knowledge, engineering knowledge and engineering common sense, because you have not studied properly. So he or she will understand you are a nonsense. Engineer without engineering common sense is a nonsense. So this is an internal construction of a DC servo motor. Same as, it looks same. From circuit model, it same as ordinary DC servo motor. Construction wise, it also looks similar, not same, but similar. Similar and same is different. Now, what is the difference between ordinary servo motor, or sorry, ordinary commercially available DC motor and DC servo motor? If you compare two motors, one is commercially available DC motor and one is DC servo motor having the same rating, then if you keep them side by side, you can identify them by visual inspection. Why? The reason lies in the design of the DC servo motor. Why? Look, in the application, that is its application in servo mechanism, what do we want? From control system point of view, we want 2 points to be, or two requirements to be satisfied by the actuator. It is an actuator basically. Servo motor is an actuator in the closed loop control system. We want two factors that should be satisfied. Two facts should be satisfied by an actuator. It should be fast. Its time response should be fast. That means its transient response, mainly rise time, settling time, all this time response should be fast. Number two, it should have very small, ideally zero, steady state error. Now regarding the first point, that is its faster operation. For that, what we require for faster operation, because it's a dynamic system, it has some time constant. You already studied the modeling, theoretical modeling of, or physics-based modeling of a DC servo motor in system theory. There you found DC servo motor has two time constants. One is mechanical time constant, another one is electrical time constant. That's why, as it has two time constant, that's why it is a second order system. There are two poles. Two time constants means two poles are associated with that. So it is a second order system. Now, this electrical time constant is very small compared to the mechanical time constant. So you have neglected the electrical time constant and kept the mechanical time constant. So approximately, a servo motor can be said as a first order system, approximately, after neglecting electrical time constant. Now the mechanical time constant, what factors affect the mechanical time constant? If you look carefully into the various equations that you have dealt with during the development of the transfer function of the DC servo motor, you found that moment of inertia plays a big role in mechanical time constant in a mechanical system. If inertia increases, time constant increases. So you have to keep the moment of inertia of the armature of the DC servo motor, which is the rotating part, to be low. How to keep the moment of inertia low? From your basic knowledge of physics, you know that if a rotating, or basic knowledge of engineering mechanics, you know that a rotating object, if its diameter can be reduced, then its moment of inertia will also get reduced. So our first attempt to reduce the time constant will be to reduce the moment of inertia. And for reducing the moment of inertia during the design of the DC servo motor, we have to keep the rotor diameter to be small, or reduce the rotor diameter. Now, from another point of, that is mechanical rotating machine, mechanical design of rotating machine point of view, mechanical design point of view. That means the if you look from the perspective of mechanical engineering design, it says that mechanical engineering design says that if you calculate the power output of a rotating machine, rotating machine, from mechanical point of view, the power output is directly proportional to the square of diameter and proportional to the length of that rotating member, axial length of the rotating member. So by reducing the diameter of the armature in order to reduce the moment of inertia, we are actually reducing the power output, mechanical power output, which is not desirable. So what is done as a designer? You should think to find out the alternative to keep the power output constant. The alternative is there, where the armature length, as I said, power output is proportional to the armature length. So you can increase the armature length. If you increase the armature length, then what will happen? The power output will remain the same, but if you reduce you can reduce the diameter, so that you can keep the moment of inertia smaller. So there is an optimization in the hand of the designer. So the designer will decide how much diameter should be reduced and how much length should be increased in order to keep the power output constant, depending upon various constraints. In order to reduce the cost, what the designer will do? The designer will purchase lamination stampings of the lamination of the laminations of the stator and rotor from the commercially available sizes. Okay, so the sizes are in discrete step, so he cannot reduce the diameter and increase the length arbitrarily. Increasing the length is not a problem. You have to just stack. You have to add more and more laminations in the stack, but you cannot reduce the diameter arbitrarily, because the size of the iron stampings are in fixed sizes. So you have to select proper size, and then you have to increase the length accordingly. I hope you already studied, you already performed some rotating machine design, either induction motor or DC motor. So you know this fact. So in this way, we can reduce the moment of inertia and make the dynamic response faster. So if you compare two DC motors, one is DC servo motor and another one is ordinary DC motor of the same power rating, you will find that the DC servo motor is slimmer and longer. Slimmer and longer. Now, the other point, that is increasing the accuracy, that means decreasing the steady state error. How to reduce the steady state error? The easiest way is to reduce the non-linearities that might be affecting the system. Non-linearities that are present within the system and affecting its steady state performance. Other thing is on which the steady state error depends is the type of the system. You cannot do anything with the type of this system. Okay, you cannot do anything. So the only thing is you have to reduce the non-linearities. What are the places? What are the places where the non-linearities could penetrate into the system? You know that in a feedback control system, if any element, any subsystem becomes nonlinear, then the entire system becomes nonlinear. So here the points of nonlinearities to enter into the system are quite few. They are, first thing is the friction present in the bearing. Bearing friction is a very significant nonlinearity. So you have to reduce the friction in the bearing by proper lubrication. Number two, if you use gearbox, because in a rotating machine, in a motor particularly, the rated speed is quite high, but for actual operation your required speed may be low but torque may be high. So what you do, you reduce the speed so that the torque increases for constant power, and that is performed with proper gearbox. Now the gears, they have backlash, tooth to tooth. When one tooth of the driving gear is being meshed or touching the driven gear, you will find some gap between the two gear tooth. That is called backlash, and that backlash is a very hard nonlinearity. So you have to select appropriate gearbox where the this type of nonlinearity like backlash is minimum. You cannot avoid backlash, but you can minimize. Definitely you can minimize the proper choice of the gear, but that will increase the cost. Number three is the choice of the magnetic material. The magnetic materials have hysteresis. So if you choose good quality magnetic material, what will happen? The hysteresis present in the system will be reduced. So it will follow the command appropriately without any distortion. So this hysteresis in the magnetic circuit actually distorts the waveform of the flux. So that incurs non-linearity in the torque generated, because torque is proportional to the flux. If the flux itself is flux density profile is non-linear, flux density waveform is non-linear along the periphery, then what will happen? The torque generated will be non-linear, and there will be undue vibration at particular angle. There will be with angular displacement. It may experience instead of uniform torque, it may experience, the rotor may experience some change in the torque instead of a steady torque. So that may result into vibration and of course steady state error. Any doubt up to this point? Now regarding the experimental setup, this entire system in our laboratory was supplied by feedback system, UK. Now that company has been taken over by some German company. So, but this setup is very old, about 30 years old, this experimental setup, but it is still working. Now this is servo motor. I have marked it. Now this is servo motor. You can see it if you remove this cover. This is servo motor is within this enclosure actually. So this is a permanent magnet type DC servo motor, but the field is a permanent magnet. Field is coming from a very powerful pair of powerful permanent magnets, and the shaft, motor shaft, is connected with a disc, aluminium disc. Now this aluminium disc is allowed to rotate or move within the air gap of a very powerful magnetic system. Here two magnets are there, U-shaped magnet, very powerful permanent magnets, and the flux is available, very high density flux density is available within this air gap. Now when this magnetic arrangement, you can say, or brake, it's called permanent magnet brake. This arrangement can be moved so that we can allow when the magnet is moved in this direction, lower direction, the downwards, if magnet is moved downward, then what will happen? The disc will enter into the air gap more and more. It will come up to this. So it will cut more magnetic flux. And if we lift this magnet, what will happen? It will come out. The disc will come out from the air gap of this magnetic brake. So it will not cut any flux, and it will rotate freely. Now what happens when we allow the disc to cut magnetic flux? So as it is a metal disc, aluminium, it is quite good conductor of electricity. So as it cuts the magnetic flux, some eddy current starts flowing. Some EMF is induced and eddy current will start flowing through this disc. This eddy current in turn will interact with this magnetic field, permanent magnet field. So that will produce a torque, and that torque will be opposing the cause. Which is the cause? Rotation of the magnet, rotation of the disc, or the rotation of the motor, because disc is coupled to the shaft, permanently coupled to the shaft, motor shaft. So when this disc cuts the magnetic flux, it opposes the motion of the motor. So a mechanical load, as if a mechanical load is applied on the shaft, motor shaft. A mechanical load is applied on the motor shaft. So by proper adjustment of the magnet, lowering or lifting, we can allow the disc to enter into the air gap, and some more if it cuts the total flux, full load is applied over here, and when it is not cutting any flux, then motor will rotate in no load. Now the motor shaft again is connected to a tacho generator. Tacho generator can perform. Tacho generator is a very small DC generator, linear. It is a very linear DC generator. It can measure the speed. Okay, so this tacho generator is coupled to the motor shaft through a flexible shaft coupling. Why? Because if you attempt to align, if you want to connect or couple two shafts, you have to perform proper or perfect coupling, perfect alignment of the two axes of the rotating shaft. But there may be, in spite of your best effort, there may be some misalignment left, and that may lead to unbalanced torque. And that unbalanced torque is actually being applied on the bearing of both this bearing as well as this bearing, and that may lead to wear and tear of the bearing and finally damage of the bearing. Now, in tacho generator is a very costly device. It's a sensor. All sensors are very costly. And the cost depends on its accuracy and measuring range. So, as tacho generator is a very costly, is a sensitive device, is a sensor. We should protect it from all sorts of vibration and other undesirable phenomena. So, we use flexible shaft coupling. So what is there? Inside there is a rubber bushing. Inside this coupling there is a rubber bushing. The grip of the rubber bushing is sufficient to prevent the slippage of the tacho generator shaft. So it can hold the tacho generator shaft firmly, that rubber bushing. But whenever any during that process, when the motor shaft rotates, if there is any uneven or unbalanced torque due to misalignment, that will be absorbed by the rubber bushing, and that will protect the tacho generator. Now, one may ask that, okay, tacho generator is a transducer, but you are using this transducer in this system for possibly some feedback. Yes, we will use in the next year. We will use this tacho generator to perform a closed loop operation in the control, servo control, that will be called speed control servo. We will use this tacho generator to sense the speed of the motor shaft, and we'll feed it back to the input side and compare it and take output from the comparator as error signal and feed it to the PID controller, and that PID controller will be applied to servo amplifier, and the servo amplifier will feed DC servo motor, and we will operate the system in closed loop. See, here the tacho generator we are using as a sensor, because tacho generator we have performed some signal conditioning, very crude, because by design this tacho generator has been made a linear device. It's a linear device. It's characteristically linear, but to prevent some noise to come out from this measurement, from this device, we have already used some filter. If you remove this cover, you will find some filters. Very small filters are present. Over and above, it is calibrated. After the very basic signal conditioning operation, it is calibrated. So you can say that the tacho generator that is being used over here is a sensor that can be used in closed loop. Proper matching has been performed with the reference input side. Now what we do, we measure the shaft speed by the tacho generator. We are using this permanent magnet to apply load, mechanical load. And here we have few potentiometers. This is a potentiometer, input potentiometer. This is an output potentiometer. During position control operation, we will use these two potentiometers. And we have attenuators. Here attenuators are also potentiometers. These are attenuator or rotary potentiometer. We can use them as a voltage divider. We apply some fixed voltage, say plus minus 15 volt, and from there, by rotating the knob, we can knob of the variable point, we can generate the variable voltage at the output of it, and we use that voltage. And a PID controller is not shown over here. I think it's a pre-amplifier. I cannot read it. This is servo amplifier. The controller, output from the controller is fed to the servo amplifier, and that servo amplifier gives power supply to the servo motor armature. So the control signal is amplified by the servo amplifier, and it supplies the DC servo motor. And servo amplifier takes power from the power supply. Okay. Servo amplifiers are linear amplifier. Its characteristics is similar to audio amplifiers. Okay, they are very costly. Their characteristics are their bandwidth is very wide, and their characteristics should be perfectly linear, so that the control signal that we are feeding to it should not get distorted. Its characteristics should be perfectly linear, so that it should not distort the signal. It should just amplify. It will increase the voltage. It will amplify the voltage waveform. It will amplify the current waveform. So it will give power gain. If we remove this servo amplifier from this circuit and directly connect the output of the control signal to the armature, what will happen? Motor will not rotate, because the current provided by the controller, because it's a signal, it's very weak. The current content or power content of the signal is very weak, so it cannot drive the motor. That means it cannot give sufficient power to the motor to overcome the initial restriction, initial, you can say, torque required to move. That means it cannot overcome even friction, although we are using good bearings, because the torque generated by the signal will be lost in the armature circuit, basically as a voltage drop, you can say. So this power and servo amplifier plays a vital role. Without servo amplifier, servo motor cannot work. Now here we are controlling the, as the in closed loop, here we will control the armature voltage by this controller and servo amplifier together. We are applying a controlled voltage at the armature of the DC servo motor. That is the point, because the field is we are not controlling the field, because it's a permanent magnet type servo motor. Sometimes you will find a servo motor with separately excited field, but that is very rare nowadays. In order to keep the size of the servo motor small, we apply very powerful permanent magnet as a field, so that we can remove the space for the field winding. Now the connection diagram, if I compare the closed loop system, the connection diagram, it's like this. Actually, during the experiment, we don't use any feedback. We are not using the servo amplifier in feedback control mode. We will use the open loop circuit. We will perform the experiment in open loop. In order to find out the characteristics, we will run the motor in open loop. How? We will use a potentiometer, okay, and use it as a voltage divider circuit. We are giving 0 to 15 volt and take some voltage at the output with respect to ground, say 1 volt or 2 volt, apply it to the summing amplifier. Sometimes if we need two signals, two voltages, then you apply summing amplifier. Otherwise, we do not use summing amplifier. You can directly take the potentiometer output to the servo amplifier, and servo amplifier will amplify the voltage given by the pot and apply it to the armature. If we change the potentiometer output, the voltage appearing to the armature terminals of the motor will also vary, but it will have some power gain, a driving capability, as it is passing through the servo amplifier. Now here servo amplifier is just, you can say, it's a valve. Power is trying to flow from power supply to a servo motor, but we are controlling that power flow using that servo amplifier. Servo amplifier is just a valve, and the command to control is getting from the controller. Controller is giving command to the valve, and the valve is operating, and power flow is getting modulated when it is flowing to servo motor. That is the actually situation here. Power is coming from the power supply, but it is being controlled by the control. It is being allowed to flow in the armature circuit in a controlled manner. with the help of a controller and by the servo amplifier. Now manufacturers have given some data. It will be useful during the experimental data analysis. What are the data given? We got tacho generator constant by the tacho generator constant given by the manufacturer. It is 2.7 volt per 1000 RPM. So as I said, it's a linear device. So if I find that the speed is 500 RPM, so the voltage will be 2.7 by 2, like that. At 100 RPM, it will be how much? 2.7 divided by 100. 2.7 divided by 1000 into 100. So 2.7 by 10, sorry, like that. 0.27 volt, like that. You can calculate how much speed is there at the output shaft. Now another characteristics is given. We are assuming that when we are applying the load torque at the equilibrium, that means at a steady speed, after application of the load, it will go to the equilibrium after transient is over, or steady state after transient is over. So then it will settle down to a particular speed. At that speed, what happens? The electromechanically generated torque will be equal to the external torque or load torque. Then only if these torques are balanced, then only what will happen? There will be no further acceleration. Acceleration will be zero, because if we apply from Newton's second law, if we apply force, first thing it generates is acceleration. So acceleration is the most fundamental mechanical quantity, motion variable. With respect to time, what happens? This acceleration gets integrated and gives rise to velocity. And with respect to time, velocity gets integrated and gives rise to displacement. So here, as these two torques, two forces or torques, load torque and generated electromagnetic torque, are getting balanced, so there will be no further acceleration, and a steady it will settle down. The rotation will be settle down at a steady speed. So from that conception, we can say that at a particular brake position, the brake position is you can see a notch. We'll see in the video that the brake position, there are various brake position 2, 3, 4, 5 up to 10. So brake position 10 means this position, the disc is fully inside the air gap. Maximum torque is being generated by the motor. This is our motor to overcome the retarding torque developed by the magnetic brake. So at 1000 RPM, this brake characteristic data given also for 1000 RPM. So at 1000 RPM, at brake position 2, the torque generated is 5 millinewton meter. At brake position 3, 23 millinewton meter, all 1000 RPM. So if you change the RPM, say 500 RPM, so at brake position 3, what will happen? The torque generated will be just how much? 11.5. Like that, you can proportionately calculate the torque generated from this table. This is possible because later we will see that the characteristic curve, which curve? Speed torque curve of a DC servo motor is perfectly linear. That is why we can interpolate the data linearly. Now let us see one video. This is the attenuator through which we are giving input voltage. This is called summing amplifier. We can add up two voltages. This is the magnetic brake. We can move it upward and downward. It's calibrated, not calibrated, just marked. You can measure the voltage generated at the output generated in the DC tacho generator. So I tried to take a picture at the bottom of this covering, but sufficient light was not there. Yes, we can measure the output from the DC tacho generator through these terminals. These terminals. So we need to connect one terminal over here and another terminal to ground. So some internal circuitry is there to perform the signal conditioning or signal processing. So this is Servo amplifier. The armature current is not being measured with this scale. What we are doing, actually we have tapped these terminals, series connected terminal of the ammeter. This is the ammeter basically. Because the scale was not very good, so we have bypassed this ammeter and taken 2 watts. Just terminals was visible from here. You can see a bit hazy. Can you see two conductors have been taken out from here? They are actually to bypass this ammeter, and we can measure this current, armature current, by some external ammeter, multimeter in ammeter mode in a precise manner. Now it is at the lowest. I think it's 5. Setting was 5, and we can increase the voltage. The voltage is increasing. At some voltage, it will just start rotating. Yeah, very small movement was there, but not continuous rotation. One meter is giving volt, input voltage given to the servo amplifier, and the other one is the current, armature current. This is the voltage and this is the current, I think. Let me check. Yeah, okay. So this is voltage. This is armature. This is armature. This is armature voltage, not armature voltage. This is actually input voltage, that is we are applying to the servo amplifier, and this is in the ammeter mode. So this is armature current. Sometimes the meter gets interchanged. That's why confusion. And this is the tacho generator voltage, that is we are measuring. So what we do during the experiment, we first of all, this. For a particular break position, we start with a highest break position, keep the input voltage as 1 volt constant, and go on decreasing the break position. What will happen at the highest break position? The maximum current, armature current, will be flowing because maximum amount of mechanical torque was mechanical load was applied. So in order to overcome that braking torque or load torque, the armature will the motor will take sufficient armature current, okay, to produce the necessary torque to overcome that mechanical torque applied by the mechanical brake or load. So what will happen? At the beginning, it is very high torque, high braking torque, so high current. Gradually, we are decreasing the load as per the brake position. So the 10 is the highest brake position, maximum braking torque is applied, and 2 is the lowest. So see, the current, armature current is decreasing. And there is also due to this phenomena, what will happen? The speed will also change. Speed will also change. Initially, because of the regulation, speed regulation at high torque, there will be low reading at the low voltage reading at the tacho generator output. So speed will be less. Now, when we decrease the brake position, the torque, load torque is getting reduced. So what will happen? The speed will go up. See, from the reading of the tacho generator, we can estimate that the speed has increased. Now you can calculate the actual torque, approximately the torque, motor torque, and the speed, shaft speed from the previous table. So these are calculated over here. I have taken this data from the repository of the control lab. Not very clear. You can also calculate by yourself from the table, using the table from these two this data and this data, this data and this data. Ideally, the theoretical speed torque characteristics of a DC servo motor should look like this: very linear, but linear as well as parallel. Characteristics are parallel. These are the armature voltages. But actually, we got this type of characteristics for 1 volt and 2 volt. Although their individual characteristics are linear, but they are not actually exactly parallel. Some deviation occurs, and that may be due to non-linearities present in the system. The next run is to find out the non-linearity, if any, present in the system. So for that, what we do, we take a fixed brake position and we continuously increase the input voltage and keep a look on the armature current reading. So we will allow the armature current to go up gradually. We cannot perform the experiment in the reverse direction. Once we have started, we will just go on increasing. We can increase during this run, we can only increase the input voltage. Suppose by mistake you have increased the input voltage too much. You wanted some intermediate reading. You cannot do that. You cannot go back. You have to start from the beginning. So you have to be very careful. You cannot go back because we are trying to determine hysteresis. So in this way, we are increasing the input voltage and noticing the armature current. And a similar manner, when the armature current has reached maximum, we will reduce the input voltage from that setting up to the minimum. And if we calculate the data corresponding to torque and speed from here and plot, you will see the increasing curve and decreasing curve. They do not coincide. So a small amount of non-linearity, hysteresis or non-linearity is present. So this graph will be useful for making necessary correction in our control law. Okay, in the control law, we can provide some corrective measure if we know this type of non-linearity present in the system. This curve will help us to take necessary action in the control law, in the design of the control law, so that its ill effect can be overcome. Now, next run will be time response. So as it's a second order system, if it is underdamped one, then we expect that this type of response and various various time response specifications are also given. We want to calculate those time. As we have neglected one time constant, that is electrical time constant, so we can say the response will not be like this, but it will be similar to first order. Actually, that is the case. This is the real response taken in strip chart recorder. And we can see that these are the noises because of vibration. This is the reading from the tacho generator. Display of the tacho generator, recording from the tacho generator, continuous recording. These are the time value, time stamp. And from here we can say this is a very similar to first order system. Now from this characteristic curve, we can find out the time constant, isn't it? So we know the initial value, we know the final value, and from here we can calculate the 63.2% rise, the time required for 63.2% rise, and that is the time constant, isn't it? That is, so I got the time constant, and from the comparison of the input and the output, I can calculate the gain, taking the ratio of the input and output signal. I can calculate the gain. So I have the gain with me. I have the value of time constant. So I can write down the transfer function of the servo motor, which is approximated at first order using this data. So this experiment will also help us to determine the model or transfer function of the system. Now these are the few references. You can follow them for more technical information. So this is all about the speed torque or characteristics of DC servo motor. Do you have any doubt? Okay, if no doubt, then I can close this session. You can write to me later on through WhatsApp in order to clarify your doubt.